Well, in reality, I'm not going to talk about QuestDB specifically. I just wanted to talk about the space of time series databases, what's going on in the space, the history of it and stuff like that, and maybe I'll show you QuestDB as well and how it fits in the whole scenario. So, oops. So what are we going to learn today? So I wanted to go through the evolution of OLAP and time series databases. So in terms of roughly the last 20 years, what's been going on. Maybe we're going to find out what data model the databases seems to converge on. And as I said, I'll mention QuestDB a little bit in the end, how we basically fit in this ecosystem. Yeah, sounds good. So a bit about me. So my name is Vlad Ilyushchenko. I'm from London. I've been here 20 years. I am co-founder and CTO of QuestDB. I guess my responsibilities are that we build things that people want. We went to Y Combinator a few years ago, and that's their kind of mantra. So we're trying not to go on the tangents and make sure that we build things that you guys want. It's not always easy to find out what you want, but you know, that's what we're trying to do. And the other thing is building databases, as it turns out, is very, very hard, and we need to do it as a team. And that's what I do at QuestDB, make sure everybody is enjoying the process, because it's quite hard work. Okay, so this is maybe a bit unorthodox introduction to time series database. So this is from what we see that organizations use time series databases to help acquire and extract information from nascent data. So nascent data is the data that just comes into existence. Some people call it real time, new data, but nascent is a good description of it. And so those are kind of pictorial examples of nascent data, what it is. So ultimately, we see a role of the database is to deliver data from the source to the user. That's basically, in a nutshell, what database does. And the sources of this data could be in the top left corner, could be financial data like trades, prices, events that are going on in the market. In the top right corner is industrial IoT. This is more of a hardware kind of applications. And people in this space, they guess what they're trying to do is to monitor the process and implement predictive maintenance, or see what's about to break or breaks, or maybe will break in the future. The key, well, quite sort of different thing about this particular approach is that usually data is being used in the custom software, so it's pulled out of the database, and they run kind of custom algorithms to basically infer some data for the production process. Data can be used in transportation or mobility, should I say. So we see these use cases arise from how shall I say? So, for example, if people develop sort of rocket engines, for sake of argument, right? So these rocket engines or engines, they dyno tested. They tested from time to time, and during the test, a lot of data is collected from the test run, and then these tests are compared. So you basically, from run to run, you compare the tests. So maybe you detect anomalies in the test, and the characteristic of this data is very high volume. There's a lot of data. Literally, some airplane engines, they produce an area of 140 million data points a second, that kind of stuff, right? So it's very tricky to collect this data. And the data probably we're all most familiar with, logs and application metrics and whatnot. So this is also time series data, or new data that sort of originates from these places. The time series data is kind of part of the big data scene. So if you accumulate a lot of time series data, that turns into big volume, big data. And there's other databases in this space, and those are OLAP databases. And OLAP databases, people use them to typically extract information from the existing data. And there's a slight subtle difference between what time series databases do and OLAP databases do, but I'll get to that later. So the design journey of both time series and OLAP databases. So very early databases, and I'm sure everybody is familiar with this, they had the quite monolithic design to them. And so what that means is, so the database looks after its own data. It defines Egress and Ingress and Egress of the database and just manages the whole scenario. So you don't see how the data looks in the storage layer of the database, or you don't have a good insight into how database does things. And then from monoliths, the databases started to move to shared disk DBMS engine. This is slightly different. I'll talk about all of these things in a little bit more detail, but yeah, I guess I'll leave it there. I'll talk about sort of shared disk. And then the next step was Lakehouse DBMS engines. And yeah, let's dive into it. So this is what monolith database is. So a user treats database as or query engine as a black box. So database owns the disk, and database also owns the catalog of your data. So in this scenario, so if we go down to next slide, so if you were to say, okay, I want to store a lot of data across my databases, so you have to split data into shards so you can host data on different servers, and doing that limits your CPU capability because your CPU capability is linked to the number of shards, and if you need more CPU, you have to reshard the data. And this is a painful process to do depending on how much data your database has. And this limits kind of elasticity because you cannot add compute resource on the fly because it doesn't have access to your data. So other potentially old things with the databases of this type, they handle all of the ingress and egress points to the database. So if you want to load data in a database, you have to go through it. If you need to query data from the database, you also have to go through it. And then basically all the protocols and code the database has could be limiting factor depending on what you want to do. And and obviously data in a database is vendor locked. So you have to get your data out from one database to another. You can do it, but it's a painful process more often than not. So in 2010s, this is the 10s, I guess. The TSBSs were, time series databases were all monolith. And they came into existence by replacing OLTP. So OLTP, Postgres, Oracle, and stuff like that were not perhaps quick enough on Ingress side, so people wanted to get more data in the database faster. So the people invented TSBS, right? At the same time, in the same decade, the OLAP databases have already moved from monolithic to shared engines. So they moved from what data warehouse was to use another type of architecture as a shared engine architecture. So shared disk engine, what is it? So the difference here between the previous slide is that the data is no longer on a disk of the actual physical computer. So this data is in object store. You guys probably familiar with object stores as S3, Azure, well, every cloud provider has it, so HDFS and stuff like that. The advantage of the shared, the shared disk architecture is that it kind of unlocks compute capacity of the database. So if you want to add another server to help you with aggregating data and stuff like that, so you can easily do that because they all share the object store. This also there's a difficulty. The things that databases do have changed as well. So object store is not your local disk, so it doesn't have random access. It's kind of restrictive to get to and from, so you cannot update it in place if you wanted it to. So the databases need to build layers on top of object store to manage access to the object store itself, to not overstep throttling or to reduce cost. So the databases have to kind of have a local disk perhaps to back object store, have a local disk cache. But at the same time, elastic compute is advantage. However, with the shared disk engine, the egress and ingress are still handled by the database itself. So all of the endpoints to get data in and out are still within the database. And data on S3 is not necessarily stored in open format. So it's going to be in proprietary formats. Every vendor does it differently. And some people make it also difficult to get data out of the shared store. So there's implementations of shared disk engine, they force you to go through the database still. So OLAP databases in 2010, as I mentioned, they already on a shared disk model, but TSBS are still behind, still monolith. The next engine that after shared disk is what people call now Lakehouse engine. The fundamental difference between Lakehouse and shared disk infrastructure is that the object store now has the catalog itself, so data catalog. And data in object store is stored in open formats. There's OLAP databases, left, right, and center. They able to read Parquet files from S3. That's what pretty much what it is. And the database architecture changes yet again because the catalog is owned by something else, something external. The Parquet files they're different to internal format. They're slightly less optimized. But the upside is that data can be put into shared storage directly to shared storage. So you can upload Parquet file to S3, and you can have database read it should you need it to. The other upside is that if you want to download data from the system, you can just pull Parquet files back, so you don't need to go through the database. And the role of the database becomes a little bit different in this environment. Is that the database is becoming more of a help to the user. For example, if you were to upload 100 files to object storage, you might want database to help you find information in these files, rather than download files and find this information yourself. But should your data access granularity is the same as your files, then you don't need to go through the database entirely. So in 20s, ultimately, a lot of OLAP databases, such as Snowflake, they moved to Lakehouse engine architecture. And time series databases are really far away from this. It's also in the past 20 years, it seems as if OLAP databases have doubled down on query performance, whereas time series databases implemented Ingress performance better than OLAP databases. One second. So OLAP databases at the same time have a lot more advanced query engines. So these query engines are effectively able to distribute SQL execution for workloads that need it. And time series, they don't. So there's no time series database with a distributed query engine. But at the same time, time series databases are a bit simpler to operate because when you have a distributed query engine, so that system is either cloud bound, so it's in the cloud, or it's kind of very difficult to set up and operate and monitor and stuff like that. So now there's a story about QuestDB a little bit. So the company was founded just on the cusp of 2020's ending in 2019. And kind of broadly speaking, we are column store with SQL engine that can do JIT compilation and some other ancillaries I'll go talk about a little bit. So it makes sense for time series database to look towards Lakehouse engines. There's multiple advantages to it. Storing data on S3 is incredibly cheap. So you can store a lot of data. Storage is tiered. It costs very little. The open formats such as Parquet, the high compressing format. And the advantage for database users is that in some cases, both Egress and Ingress can bypass the database entirely. So you can have a scenario where you can upload Parquet files and have database query them. So you don't need to go through the database to do it. You don't need to convert formats. You don't need to specialize to have special drivers or anything like that. So Parquet files in, database reads them. And as I mentioned before, the database role becomes a little bit of a help. So where database is able to search your files should you need it to, or just stay aside if you're happy to get files in and out. And one thing that sort of Lakehouse engines also tend to do is to kind of focus on unstructured and semi-structured data as well, which time series don't typically do. And this is JSON data, array data, and stuff like that. So our goals kind of change because we've been in this business 5 years, and we need to kind of look around to see what our goals should be. But it kind of makes sense to address for us to try and address the gap between time series database and OLAP databases. And that is by having high performance ingress, what is essentially a column store. And a column store is a data structure that is that's built for queries. It's not built for writing data to, it's built for queries. And having high performance ingest in such a data structure is fairly unique thing to have. We want to build distributed SQL engine, so we can run workloads across, well, business intelligence workloads across multiple servers should we need to. And we want to have high performance egress. So the high performance egress, I'll talk about that a little bit more on another slide, but it becomes quite important in age of particularly AI, when data is kind of extracted from a database into Python and processed kind of in bulk somewhere else outside of the database. We also wanted to make things quite simple for the user, so eliminate needless complexity. I should say the database itself, we built it from scratch, so there's no dependencies on it, so it's built ground up to be high-performance database. And we want to keep it this way, even though we're going into Lakehouse era and distributed queries and multi-nodes and stuff like that. So how do we do that? So the Ingress APIs. What's quite interesting about Ingress APIs is that most of the data in new data is row first. So data that originates from sensors contains multiple columns on one line. It's a row first. It's the opposite of column first workloads that OLAP favor. And we want to provide maximum performance, Ingress performance on these type of workloads. The Ingress should also balance hot and cold partitions, and by that I mean automatic partitioning, and I'll get into that on the next slides. It provides schema elasticity. What schema elasticity is that you can, for example, add a column on the fly to the database. So you don't need to, you don't need necessarily to have a separate out-of-hours script that adds a column before you can change your publishing code that publishes values in this column. So database effectively guarantees consistency if you've got 5 publishers or 10 trying to add the same column to the same table. So they're all going to succeed, and one column is going to be there in the end. And the Ingress should provide data concurrency and high availability. So what that means in a high availability scenario is that we want our Ingress to be highly available in terms of you can send data to more than one node. So if you fail to send data to one, you can send data to the other. And here there's some scenarios. For example, you send data to one box, and this box doesn't reply. You basically have a timeout. So there's no certainty whether the data that you send is actually in the database or not. But instead of your application failing and waking somebody up in the middle of the night, you can just send data to another node. And the guarantees the database provides is that this data will be inserted only once, even though you didn't wait for the previous batch in one machine and you send the same batch to the other machine. Data will be just once, pretty much, and you don't have to worry about fixing the process, pretty much, if should this happen. So how does Ingress work? It's kind of simplistic diagram, but what I wanted to emphasize here is that we use write-ahead log, right? So the database writes data to write-ahead log first. So write-ahead log is for all intents and purposes is a append-only structure. There's only basic validation that is performed when data is ingested. So this write-ahead log is basically fronted by different network protocols. So you can put data in write-ahead log from CSV. We support influx line protocol. We could send arrow in, and basically the different data formats. Some data is row first, some data is column first. And ultimately all of this data goes into WAL, and WAL is asynchronously applied to the column store. And the reason I mentioned row first and column first is because a lot of databases kind of experience this kind of ingress-egress paradox, where they're trying to insert row first data into column first data store. And when this might not be a problem kind of when you just do basic benchmarks, but it manifests itself as a problem in scenarios where your tables become quite wide. So if the table structure is such as got 500 columns, or maybe you've got a lot of tables with small number of columns, so ultimately what this kind of converges to, you do a lot of random writes to disk, and these random writes start to bog down quite rapidly. And just to avoid this, by the way, so to avoid this, what we do is we have a mixed wall write-ahead log format. One is for row first data, one is for column first data. So the row first workloads are written to row by row, and column first workloads are written column by column. So we kind of mitigate. We don't entirely remove random writes, but we mitigate it quite well. So the balance in hot and cold data. So what typically happens during ingress, heavy ingress workloads is that disk space is consumed quite rapidly. Basically, that's what happens if you send a lot of data to the database. And the job of time series database, and that's what QuestDB does, it effectively automatically partitions your data on timestamp as you put data in, and offloads these partitions to object store as you create them, and it recompresses them in Parquet. And the files become available for reads, but ultimately database is able to sustain high volume of load without running out of disk or costing too much or firefight the disk space as data is ingested. The new data, as I mentioned before, it comes in a write-ahead log formats, and sort of these write-ahead logs are used to join. Well, they can be replicated to S3 as well. And what that gives, it gives kind of ability to another compute node to have visibility of the old data that is already in Parquet files on S3, plus be able to reconstruct the hot partition that is locally to the machine. So you can have multiple compute nodes looking at the same recent data. Okay, data concurrency. So I guess you guys familiar with MVCC. So it actually wasn't apparent to me for a number of years that databases are not necessarily override the data. They're copy on write systems. So every time you modify something, database copies data. So, and then database tries to manage the size of the block that copies. And actually, incidentally, from this there's a terminology called write amplification comes in. So you write a little bit, but because database needs to write a block of copy data, copy and write bigger blocks, so you can have more physical disk reads versus how much data you actually written. And the same goes the other way for reads. But yeah, so as any other database, QuestDB can read data that's being written, so quite transactionally. The column store itself is also ordered by time. So the database will be sorting data as it reads, and it needs to as it writes to it, and it also keeps it consistent. It provides the concurrent update to Parquet files itself. So all partitions that have been deposited to object store, if you send data to them, the system will update them as well. And it also provides concurrent metadata changes and data republish after network glitches is what I mentioned before. So you can republish the same block without duplicating data in the database. So how this metadata consistency works. With data written to write-ahead logs, after transaction when transaction is about to be committed, we have an entity called sequencer. The sequencer is very similar to what other databases have. They store it in zookeepers and stuff like that. So the sequencer has the metadata of the table. So it has transaction numbers, it has number of columns, it has a list of partitions and where those partitions are. And the idea here is that if the column is added concurrently by two actors to different WAL files, so there's a version control used to basically before WAL is concluded, we check the version of the write-ahead log versus what sequencer has. And if the write-ahead log version is lower than the sequencer itself, that means there was a concurrent update to the metadata that the WAL has to reconcile the entire transaction. The advantage of doing things in this order is that if reconciliation were to fail, the error can be reported back to the user as an error, right? Or write-ahead log can successfully reconcile the data. For example, if a column is added which is irrelevant to this transaction, it will populate column with nulls and insert it in the database. So this mechanism effectively provides the ability to add columns pretty much on the fly without locking the database or taking database into off-peak mode of some sort. Now, Egress API. So this is what we saw throughout the years, what people do with time series data. So one use case is to for Egress is to power BI software. So it's analytics, it's aggregations, it's top of this, bottom of that, kind of pie charts and stuff like that. So it's analytics. Sometimes they zoomed out as well, so user can zoom it out. That causes the database to go over larger volume of data. And this is type of workload that it requires effectively distributed queries, because everybody wants data fast, no matter how much data you have. And if somebody zooms out 5 years up, then database needs to do a lot of calculations to do it. That's the prime case for OLAP and distributed query engines. Some other workloads are time series workloads. The time series workload is basically charting, time series charting. So people plot a chart of something that is more likely to be very recent, and trips into the past from a charting applications are quite rare. And what's important there is to optimize execution, query execution, on a single CPU kind of stuff, because going across to multiple machines could be prohibitively expensive, depending on basically on the query. Other types of workloads, such as Spark or Python, they sometimes these workloads need to execute data on a SQL, definitely. But a lot of other times, these workloads just want to access object store directly. They don't need to go to the database, and this is where database bypass becomes interesting and important in this scenario. And so the workloads the workloads that offload quite a lot of data to the database actually necessitate a different type of egress API, such as Arrow driver, ADBC they're called. And this is what and this is the problem. Rather, the problem these drivers solve is to get data, large volume of data in or out of the database over the network requires multiple network connections. So a database is not necessarily going to scale linearly as you add more network connections to them, but doing it over a single TCP socket is not going to happen. And this what ADBC driver provides. So your output data is split into column sets. Those items are still columns, they're just smaller in size. These columns send back to back over the wire to the client, and then they reassembled into larger columns. And all of this is abstracted via SQL execution. And typical examples here for time series workload, somebody would just query data on an interval. Say they want data for past months. That's basically, or maybe some filtered data on a predicate. They want data for past month for this particular time series. And it's common in time series database to put multiple time series in the same table. So you would be filtering a time series out of a table to a client. And that could be quite large data set. So sending it over multiple network connections implicitly makes a lot of sense. And this is what ADBC facilitates. And the SQL engine is effectively a reflection of the workloads that put on it. So it executes. It's typical for OLAP, and it's what we do as well. Is to execute group by, order by, and where clause concurrently. So when I say concurrently, it's executed in parallel. So data is split into chunks. Those chunks evaluate in parallel. Data is merged back. And to optimize this, we also compile some of the predicates into assembly, which is AVX2 assembly, and to avoid costly function executions. And this helps with analytical workloads. It helps with time series charting and helps with BI workloads. The SQL language extensions such as sample by and limit. So we kind of offer these things. I'll show examples kind of later on, but these are simplifications that take advantage of data being ordered by time, and sample by is a group by on a time interval, and limits allow you to pick particular data in a time range quite easily, and I'll show you how to do that. The SQL engine also leverages metadata layout for metadata and data layout for query optimization. And a good example of this is that if you have data that is, for example, rank length encoded in a column, right? It's not necessary to materialize this data back in memory to perform a where clause search on it. So you can search compressed data without uncompressing it. This is what optimizer tries to figure out, data layout and what kind of execution algorithm to pick. Interval search is used to send bulks of data to either to Python or maybe kind of to chart. It also uses leverages layout or ordered layout of the data itself. And the data internally is represented as a column first for query engine purposes. Such data makes it relatively simple to offload it to ADBC driver because it's a column first driver. And this is before I wrap up. I kind of went through it quite quickly, but before I wrap up, this is examples of sample by queries. You could potentially write a group by statement here, kind of by truncating date to hour, but this is simplification. It does the same thing. And in this example also there's interval query. Kind of instead of expressing it via date between X, Y, Z, this is 7-day interval of 1st of June 2018. This basically this is semantically easier to write SQLs. Oops. So this is example of as-of join. So as-of join is a time series join. It joins the data on a fuzzy time interval. So a typical example would be to find a value from another table that happened before. Well, if you've got table A and B, you find the value in table B that happened just before the value in table A. So that's what as-of join does. And this is time axis travel that also takes advantage of the order of the data. So the first example just shows the last 100 rows from a data set. So this is the illustrates like a negative limit you can use on the queries. And the second example is okay. So it uses keyword latest. So it finds latest version of the data in that particular day of 2018, 5th of April. So, and it partitions this data on, this is the trips database and the trips of taxi trips database, and the cup type is has one of two values. So ultimately this would go mid the data set and pick the latest data for a given time interval. So you can version your data essentially, and this executes it's quite quick and takes advantage of the ordered data set. So to wrap this up, the Lakehouse seems like the engine everything is converging to, and it looks as if OLAP databases they converge. And OLAP and time series databases converge on the same target. OLAP are improving their ingestion pipelines. They trying to do implement streaming workloads into OLAP databases, and TSDBs are trying to improve data storage, make queries distributed, and deal with large volume of data at the same speed as OLAP do. And ultimately, they will, well, we don't know the future, but they might become one because they're all moving in the same direction. In the meantime, time series databases and OLAPs coexist in the way that time series database ingests data, new data quite well, and this data then offloaded into a bigger database and analyzed for posterity in OLAP database. That's I went through it quite quick. That's all I have. Thank you, guys. Thank you.
Thanks, Vlad. We do have time for a few questions. Anybody have any questions? We can start from here.
Thank you very much for the presentation. I had two questions. One with time series databases. One is out-of-sequence events.
Yeah.
How resilient is QuestDB to handling that? The other one is, so you obviously have streaming input, Ingress, but do you also have streaming egress on Quest?
Yeah, so we're building streaming, it's not streaming egress, but we're building this ADBC driver for large volume egress, so it's not quite streaming. So the capability, as a streaming egress can be achieved through the change data capture. These write-ahead log files can be shipped somewhere else and analyzed. It can be done like that. So in terms of out of sequence events, so we call these things, well, internally we call them out of order. It's kind of the same thing. So as I mentioned, the database is, well, our database, not an exception, is they do copy and write kind of stuff, right? So you are allowed to send data as far back as you want. It depends. In some patterns would perform quite well. It depends how much data we need to rewrite. But there are some degenerative patterns basically that they're gonna go in very slowly. It depends. For example, if you're causing small transactions into like a top of a partition and we're overwriting a big partition over and over and over, so you can get into this kind of scenarios. So broadly speaking, yes, you can send out of sequence events. We try to, in some cases, split partitions if we detect this kind of event. So the big partition gets split, so we overwrite only smaller chunks. But ultimately, there's a possibility to get database in the corner with this kind of things. And I'm sorry, you asked another question as well, and I forgot what it is.
Just two questions.
Okay.
Streaming egress, yeah.
Cool.
Thank you.